that was amazing. That was absolutely amazing. And I'm glad that we recorded it. You did go through fast, but you covered an amazing amount of ground with it. So I promised Mr. Sarfatti that I would put him on first. So let me ask him to unmute now.
Hey, Jack, you're still muted, by the way. There we go.
Okay, can you hear me? Okay,
Yeah.
I must congratulate. I must congratulate you. That was a really good talk, and I actually had some good ideas in there. And actually, I learned a few things from you here. That's right. About the connection between the metamaterials with scale invariance and conformal gravity. Yeah, that was good.
Right. So your idea of getting this scalar field, I was kind of getting an email debates with Jack, and I was like, hey, you're kind of claiming that this scalar field is going to give you some renormalizability. No, I call crap. That's not going to work. And so I started thinking about it more, and I realized, I was like, well, these conformal gravity people, I was like, that's what we need to do. And then I thought about it more, and I realized, well, they have this scalar field, and it's very similar to what Jack's doing. So
yeah. So I see that now. That's very good. Let me just make a couple of comments on the earlier parts of your talk. As it turns out, I first suggested elementary particles as extremal black holes back in the late 1960s, early 70s. When I was working with David Bohm at Birkbeck College, University of London. I actually published a little paper in Nature Physics at the time, Nature Physical Science, a little letter on that. So, and what I want to point out is the only way, and that's good about the Cartan radius. I have to learn, I don't know that math as much as you do. We'll have to discuss that. But the point is that all this requires the Bohm interpretation of quantum theory, not the Copenhagen, because with the Bohm, you actually have particles, whether they're strings or they're extended, the torsion, all that stuff. And then you had something with about the 14-dimensional thing. I have to see that in more detail. You send me your PowerPoint, okay? I want to see the whole thing.
For sure.
But then you talk about the two rotational angles.
Mm-hmm.
Yeah, with this 14.
And this isn't my idea. I mean, this is coming from Wilczek and Z.
Okay, well, it turns out that's what's his name? The Russian guy has the two angles. Shipov, Gennady Shipov's torsion theory.
Oh, interesting.
He has. So it's okay. So
a lot of people have studied similar things. That's the cool thing. There's a lot of different ways to interpret the mathematics. So a lot of people miss some of the effects, but then study the right mathematics.
Yeah. Okay.
So it's very interesting to look at it all.
Okay. Another point where you're talking about the gravitons inside the metamaterials. Same speed of light, same as the speed of light, and all that. One important thing, which I think is happening, what the Froelich effect does, it's a kind of Higgs mechanism, and actually, it's like a gravitational superconductor. Just like as you mentioned, the photon gets mass in a superconductor, but because of Froelich pumping, it turns out that the graviton also gets a mass inside the metamaterial from the pump. But you see, let me just say, what that explains why the Tic Tac does not have a big atmospheric disturbance outside it. See, because all the exotic gravity effects are localized inside the fuselage of the Tic Tac because of the finite effective mass of the graviton from the Froelich pumping effect. So it all makes sense. It all fits together.
Yeah, definitely. And I mean, I think that's the important thing to stress. We're not going into some exotic theories. We're sticking to the mainstream conventional,
conventional stuff. And of course, now I do see. I was kind of resisting your, going into the exotic conformal field theory, but I think that's a good idea now. Now I see what you're talking about. That's good.
Well, and if I could jump in, so now, Jack, now that you finally made it to our conference, of course, I would love you to present. And I think that you've said that you may be open to that in like late February, perhaps March.
Yeah, with Keith Wanza, but
yeah, that would be wonderful.
We should probably have Chester on that also, because he has a good knack of explaining these complicated things in a pretty clear, simple way. I was very impressed. Very important.
Wonderful. Well, and again, David, thank you. And Jack, thank you for joining us and contributing. So let me go to Jeremy Reese now. He has his hand up. Jeremy?
Oh, first, I'd like to thank you for joining us. You covered a ton of ground, and people were saying you were talking so fast they couldn't. Some people were having trouble keeping up at some points. But that was great. You have to speak fast when you're unloading that much information. That was just it was like some people were commenting that I feel like I just had 6 months of schooling.
Well, good, yeah, and it is recorded, so hopefully people can listen again.
Yeah, and then go back and first off, I want to know if you could make a copy of your slides available in PDF for our audience, and I could link to that. That would be great.
Yeah, I can do that.
Going way back, I suppose to Einstein and some of his colleagues like Wheeler, and Wheeler, of course, worked with Bryce DeWitt. Were two names you didn't that. I was hoping you could comment on some of their work and some of their research. I noticed a paper that I found in some of my research, 1966, on rotating superconductors and gravitational drag by DeWitt. And so it looks like they were, in fact, researching this stuff as early as the mid-1960s.
Yeah, definitely. So I can make contact with that. I mean, there's this Wheeler-DeWitt equation that's studied in quantum gravity. And obviously Wheeler was interested in this geometric dynamics and really introduced this wormhole concept. So yeah, when I briefly sketched the ideas from Maldacena, that was building off that work. And to me, geometric dynamics is the same thing as unified field theory, or like gauge gravity, unified quantum gravity. I mean, there's so many different ways you can say it. It's like you can call it twistor theory, you could call it string theory, you can call it supergravity. I mean, broken, maybe the supersymmetry is broken. We don't have to get into that. There's all these different names. So at the end of the day, Wheeler had this idea that everything is sort of made of the same stuff, right? And that is the idea of Einstein, to unify everything. So I definitely believe. Yeah, and then getting into the quantum mechanical interpretation, focusing on the information. So then we can get into arguments, what's more fundamental, so the information perspective versus the physical stuff itself. But it's definitely related here for sure.
Another thing I wanted to point out, Sabine Hosefield, she's got a real popular channel. She's a quantum gravity theorist on YouTube. I don't know if you're familiar with her. She did a recent video talking about warp drive, and she mentioned a paper by Alexei Bobrik. I don't know if you've ever heard of them or heard of any of these people.
Okay. Yeah, I mean, I've heard of, was it Hossenfelder? But yeah, I mean, I know she looks into superfluidic dark gravity, which actually might be vaguely relevant for some of this stuff. So that might be why she is interested in those types of things. But I haven't looked into those details. So yeah, I mean, I'd be interested to look into more. I have to admit, obviously, I don't mainly look into anti-gravity effects, but I've just kind of been following the story enough where, I saw what Jack was doing and figured I could explain it. So yeah, I'm interested to look at a little deeper. There's definitely more stuff out there that I haven't seen.
Right. And then I have another thing. My final question was about entanglement theories of gravity and kind of how some of these guys really. I noticed you mentioned Polyakov. There's another physicist who posted on some of these forums named David Waite, who's contacted me, and he's got a channel as well. I don't know if you've ever heard of him, but he's got some interesting tensor transformations and has done some work in C tensor on some of this that I thought was interesting and relevant. I was wondering if you had heard of him either.
I feel like I might have heard the name, but I don't remember right now what he's worked on, so I can't really comment. I just thought of another thing in terms of my perspective on the Wheeler-DeWitt equation. They had this idea that there is no time.
Right.
And that is sort of this quantum mechanical thing. So in terms of my investigations,
quantum, it's called quantum non-locality too, right?
Yeah. So I mean, some people, like some string theorists, compactify everything to a point, and then so it's like there's no space. They're trying to get this information theoretic thing, and you get this idea that there's the quantum wave function, and then there's this universal wave function. And really, if you zoom out to everything, it's just this pure state that isn't evolving. It's very similar in thermodynamics. When you have a steady state solution, it doesn't evolve over time. It just stays in the same state. So then it's kind of like there's no time evolution. There's no time because it just stays the same. And so that idea has gotten into the Wheeler-DeWitt equation. I mean, it's because they get this Hamiltonian where it's just equals 0. And so it's kind of a joke. Well, not a joke. I mean, people take it seriously, but it's like this theory where it's like, okay, the answer, it's like, what's the theory? It's like H is 0. It's like, what? Okay. You know, so that's why people like talking about it too, because it sounds a little curious. But I think with the multiple time dimensions, it changes the story a little bit. And there's some, I haven't published it yet, but there's some math I'm working on where basically the Wheeler, when you go into extra dimensions, it gives you extra terms. And so the time dimensions gives me like I get 3 mass eigenstates for the different masses. So those end up coming into my Hamiltonian. So when you basically study multiple time dimensions and embed one time in multiple times and then reconcile causality, the Wheeler-DeWitt equation can be modified so it actually isn't 0 anymore. So, I mean, this is obviously not published yet and something I'm just starting to look into, but small comment.
Awesome job. Thank you again. And everyone now watching, smash that like button and share this. This was the best one yet. I swear. This is great.
Yes, this is wonderful. And Jeremy, thank you for the question. So let me go to Mark Fiorentino next. Mark, there you are, sir.
Yes, hello. Yeah, I had a question. If Einstein was alive today, would he agree with this statement, gravity is equal to a contraction of space?
I mean, I guess he would just have, I mean, he had the curvature. I think Einstein would really be interested in the fact that in metric affine gravity, there are 3 different equivalent theories of general relativity that have completely different perspectives, and they give you the same math. So what we're finding in quantum field theory is there's all these different theories. The concepts look completely different, but in rare cases, you can get them to predict the same thing. So that really makes you start to think about how much does our conceptualization actually even matter? You know, these people will cling on. It's like, I have the right concept. I'm thinking about it the right way. But it could turn out there's multiple ways to think about it that get to the same result. So, and I think this is really at the notion, generalizing the notion of coordinate independence and unifying it with gauge theory. Einstein really almost invented gauge theory with teleparallelism because it turned out to be a gauge theory. So I think he would realize that he would look at the other forces of nature and be amazed by how many different ways there are to describe it, and hopefully be open-minded enough to consider multiple explanations. That's kind of my cop-out answer.
Well, are you familiar with his happiest thought concerning general relativity?
Let's see, what was his happiest again?
Einstein followed a line of reasoning that began with his happiest thought of his life. Still at the Swiss Patent Office, he conducted one of his famous thought experiments. Einstein imagined a circle spinning in space. The center of the circle did not move, but its circumference was moving quickly in a circular direction. Einstein compared what happens in several reference frames, which is a standard tool he had used in developing the special relativity theory. He concluded, using his special relativity, that the boundary of the disk contracted as it spun. There was a force acting on the circle at the boundary, the centrifugal force, and its action was analogous to that of the gravitational force, but the same contraction that affected the outer circle left the diameter unchanged. Thus, Einstein concluded in a way that surprised even him, the ratio of the circle to the diameter was no longer pi. He deduced that in the presence of a gravitational force field, the geometry of space was non-Euclidean. So he got the idea of how to bend space mechanically, physically. So that's what was inspiring him to confirm that in his mind, it was a contraction of space, and he had a definite mechanical mechanism to do that. So that's why I think it was
okay, Mark, you said it enough already. We don't need a lecture in elementary, you know, this is off topic. It's okay, but you know.
I don't think it's off topic.
Yeah, no, it's an interesting point. There is actually a lot of interesting controversial ideas where you even think about material, these types of materials, and you rotate them very fast. To actually go through calculating all that is kind of interesting to look at, and I think that is intimately related to you're actually hitting on the point some of the things related to the torsion aspects, because if you have a really high spin density,
I'm glad you brought that up. Excellent.
So I mean, at the end of the day, you have to look at the most general mathematics for differential geometry, and Cartan helped bring some of that, and that might be relevant for reconciling angular momentum conservation, especially if we have quantum spin. So yeah, I mean, I think, yeah, that sounded great.
So yeah, that is basically the angle I'm working, and I use the moment of inertia equation to work out the problem of gravity.
Yeah,
And
well, I think that's wrong. Let's.
I think a lot of physicists,
Somebody else talk.
would say that, yes, but I don't believe
Also, by the way, Einstein's happiest thought in the literature has to do with the equivalence principle.
That was another happiest thought.
Not with what you were talking about, although what you're talking about is also important, but
Yeah.
it was not generally called Einstein's happiest thought. Was
I just quoted it from Amir Excel's book.
From who? From which? From who? You quoted from where?
Amir D. Excel.
Say it again.
He's a physicist. He wrote the book God's Equation.
Oh, okay. Okay.
Yeah. Well, then he got it wrong. He got it. It's not quite accurate. The happiest thought was when the guy fell off the ladder in the tower. He was painting the tower in Zurich, and the painter said he felt weightless when he was falling, and that's what inspired Einstein with the equivalence principle, which was one of the several important ideas leading to the general theory of relativity.
Well,
so to connect those ideas, I just want to say that studying the equivalence principle in the most general differential geometry is very interesting. And that's what gets into these equivalent theories. And yeah.
Well, doesn't the equivalence principle connect acceleration to gravity?
Sure, yes.
Sure.
Yeah.
Well, let me, sorry about that. I've got a bunch of different messages kind of conflicting with each other here.
Let's keep it coming.
Yeah, well, so one person, and I'm not sure where it went. Oh, Rob Chambers had asked about Einstein, Cartan, Evans theory. Ron, do you want to unmute yourself, Rob? There we go.
Evans, is it
Rob Chambers,
hello?
sorry. Yeah, Rob, you there?
Hello, can you hear me?
Yep.
Yep. Okay. No, it's just something that that I remember from someone who's tried to apply Cartan theory, although I think it's still quite a classical theory, and it's not well. I don't think it's very well known or well supported necessarily. I don't know if it.
Right. So the Einstein Cartan Evans theory. Yeah. So I actually have looked into this a fair amount. So this is, I would say, inconclusive, because it gets to a point where it's clear that there's a lot of work written, and let's just take a bet there is a typo somewhere in this work, because even the best textbooks have sometimes hundreds of typos. It gets to a point when you read their work, it's honestly very difficult to tell what they're talking about, because there's so many subtleties, and they have to really carefully define their notation. That is one of the biggest problems I find with their work, because there's so many bold claims, and they're discussing maybe interesting mathematics, but they definitely get some things wrong, like very basic like ideas about what gauge symmetries are. They're thinking of interesting ideas. I mean, I looked into that stuff, and it honestly motivated me to revisit Maxwell's treatise. If I didn't hear about Tom Bearden, for instance, I probably would not have read Maxwell's treatise. So I want to say that to say I'm open-minded, and maybe it's slightly inspirational, but obviously it's a very controversial theory, and it has too many bold claims. It's not very productive for most scientists, because it's taking too many leaps, and there might be some good ideas in there maybe, but it's hard to tell how to really get to simplify what's going on there. And there seems to be a little shady, I don't know, the way they co-authored papers was a little bizarre at times. It's hard to know. I don't know, there could be some dishonesty there, but then Tom Bearden got this patent in the US, and it's very difficult to get the patent that he got. You need someone to confirm an experiment, but it's very mysterious to me. So I don't really know what to make of it, to be honest.
Yeah, same here.
And I don't think it's productive to try to, honestly, it's more productive to do it right. And, if you want to read that stuff, great, and try to figure out how to do it right, I would say.
But the Evans is a waste of time. What's his name? Jared Hooft really knocked it down, at least his electrodynamics. I didn't realize he had a gravity theory too. But that whole alpha, you talk about the alpha group in Budapest.
Yes.
No, they're just forget that. They're very. There's something very strange about that whole thing. Because they also Vigier, Jean-Pierre Vigier was part of our group with Joe Firmage at the ISSO back 20 years ago, and they used Vigier's name in a paper which Vigier didn't even know they did it. So there was a lot of dishonesty there. It's a waste of time, unnecessary.
Yeah. Okay. Thanks.
Let me see. I had another question here, and I'm not sure who was asking it, but he was asking if you had seen the Hutchison effect videos. If you had any thoughts on those. And I believe he was probably talking about the gravity part of it.
Yeah, I mean, once again, I think there's a lot of interesting tinkering going on there. I mean, I am willing to believe that some exotic effects are occurring in his laboratory. But, once again, I just haven't really looked into the details enough to really understand, okay, what precise effects are, because a lot of that stuff is just like you see levitation of some very light object. So it's very difficult to identify what is actually happening there. Is this just some electromagnetic effect, or is it actually a gravitational effect? I suspect a lot of his stuff is just, exotic electromagnetism and doesn't really make contact with gravity, but I don't know. So, yeah.
Okay.
It's uncontrolled. We can't do anything with Hutchison. It's too uncontrolled.
Yeah.
We don't need it anymore. We have a pretty precise path now to understanding the tic-tac. By the way, Frank Milburn is here, I think. I see.
He is. And
he's on video.
I am here, guys.
Now, would you guys like to go, because we're kind of invading David's Q&A time, and so I don't want to drive everybody nuts, but then I also appreciate your being here, and as well as Frank.
Fine with me. Whatever. You guys think is best.
Here's the thing Tim Ventura and Frank did a video last night, I think it was, on the military threat, because we are interested now in the tic-tac, right? We're interested in the U.S. Navy close encounters with these objects and how to understand them. Okay, so and here Frank is here. He's the military. Frank, were you British Army or British Air Force?
I was in the British Army. Is the sound okay, guys?
Yeah, you're
decent enough.
Yeah, I was in the British Army, but I served basically across tri-service, so with Navy, Royal Air Force, Army.
Yeah, okay. So yes, and the thing is this: don't you think we should take advantage of Frank being here, because really, a military problem, isn't it? And we're talking about the military threat of this advanced technology.
Well, and so I guess what I'm wondering is maybe we should schedule that in. What we had coming up next, now, I mean, we are ahead of time, and so I guess I should square this with the conference to see how everybody feels about it. But I would be open to it. I mean, David ran fast, and then I think we went through the Q&A pretty fast as well. So,
just to make a comment on that, I would say that let's not get into fear mongering. Honestly, me personally, I'm more interested in, using this technology to solve problems for humanity. I think one of the biggest problems is transportation, right? Like, think about it. We have hunger issues. We have enough food. It's about getting it places. I don't think we should do this. I mean, okay, if we want to protect from an interplanetary threat, sure. But what's the probability of that, realistically? I think there's more short-term benefit for humanity for other reasons that we should be focusing on.
It's not a zero-sum game. They're both connected. I mean, yes, of course, if we have the tic-tac provides a support mechanism. With Tic Tacs, with low energy warp drive, we don't need jet engines. We don't need gasoline engines. That's pretty obvious. We don't need rockets. Well, we have we have warp drive. You see what the Tic Tac can do.
Well,
yeah, the other problem is
day.
there is that, yeah, sorry guys, you can't it's good to benefit mankind, absolutely, and I wholesale agree with that, but also as well, you can't afford to stand still while China and Russia go ahead with this technology and then leave the US behind, because that's going to have a very, very bad outcome.
Exactly.
Don't get me wrong. I think we should push forward with this for economic reasons, for sure.
Yeah. Okay. So I think we're all in agreement on the peaceful uses. We're all in agreement.